Okay, so today we start the ninth lecture, and we will talk about linear regression. So at this point, we already have studied some tools of machine learning. We talked about Python, NumPy, Pandas, and so on. We talked a little bit about statistics and probability theory, and we have even considered a classifier, a naive Bayes classifier. And now we are getting to our next topic. It's linear regression. As you might remember, then when we are talking about so-called supervised learning, there are two sub-branches, so-called classification and regression. So we already saw how classification looks like, and now we are getting to regression. So what is the difference between classification and regression? So such a simple question for you.
Classification is discrete, and regression is continuous.
Labels are discrete in classification, and as Fedor said, labels are continuous in regression.
Yes, absolutely correct. So when we are talking about classification and regression, the first thing that we are considering is whether our classes are continuous or discrete. Discrete classes, classification, continuous, regression. So today we are getting to regression, and I will show you maybe the simplest, simplest possible regression. You have probably seen that. You have probably seen the ordinary least square regression, but I have a hope to show to you this instrument or this tool, if you wish, from the site. You probably have never seen it before. So I'll try to maybe skip some equations to not overload you with all these formulas. But anyway, there are quite nice things that I want you to show and I want you to see. Okay, so let's get started. So this is a very old method. So Legendre published the method of least squares in 1805. So that was quite a long time ago. So what is the exact problem? If you have studied that in a course of calculus or whatever, you have probably seen something like this. So you have some x's, you have y's associated with that axis, and you want to draw a line that minimizes some sort of error. And this error is often given by this sort of formula, like SSE, sum of squared training errors. And here you see that you are basically taking your model. You are finding the difference between the exact y's and whatever your model predicts. And then you are, calculating the sum of squares of those errors. So here you see an example how that looks like in a geometrical sense. So you have a line, you have some sort of points, and you are calculating the distance from these points to the line, and you are taking squares, adding everything up, and you get your total error. Here is another geometric perspective that basically shows you how all that squares look from a geometrical point of view. So you can draw a square that one of its corners, it's the measured point, and the other corner lies on the line of regression. Well, a little bit philosophical question for you. How do you think, why do we take differences along only y-axis?
Because y is dependent also on x, and it's probably some needed data.
Mm,
Probably taking the normal distance would be
the thing is, actually, that this goes in line with how do we think about our model. So what needs our model to do? So I'm creating some sort of model. It's some sort of black box. I'm putting some X into there, and it gives me some Y. What is the most natural way to say whether this box works good or it doesn't work good? It's basically to put an X into there and look how different is the Y that you get from the result that you expect. So the main thing is these X's, they are not symmetric. If you are thinking about calculating some sort of normals or something like that, you are making them symmetric. You are making them equal, but they are not. Because one of these X's from X and Y, it's a feature. The other one is a class. They have a very different meaning. So this is like, let's say, functional difference between these X's. So one of them is the result. The other one is the input. They are not equal. They are different. When we will be talking about different methods of machine learning, for example, we will have PCA, principal component analysis. We will have a very similar situation, and we will calculate basically distance with respect to normal. We will do that. But in PCA, these two axes, they will both correspond to what? How do you think?
Influence of some
The features.
features.
The features. Yeah. So in PCA, we will have features. Our both X and Y will be features, and we will be doing some calculations, and you will see basically almost the same like regression-like computations, and we will have normals here. We will see that. But X and Y, they both will be features. In the case of regression, X is the feature, Y is not. It's a label of the class. It has a very different meaning. So it's not symmetric with respect to changing X and Y places. So if I switch places some features, it's basically, it doesn't mean anything. Who cares? Do I measure, for example, first distance along this axis and then along that axis, or I do it another way? So it doesn't change anything basically. So you can switch feature places. What of that?
because they're different scale on one of the axes.
Yeah, so if these axes are different, I can imply some different operations along these axes, and that may be pretty okay. While in some different cases, I may expect some symmetries to be held, and I can do that in there. So yeah, it may be the case. Okay, so hopefully we are clear with that. So please keep in mind that one of these axes has a very different meaning from all the rest, because we will be talking about linear regression in case of many features. And so you probably may want to keep in mind that axis that corresponds to class is quite different from all the rest axes that correspond to features. Okay, not getting too deep inside, you probably have seen that in calculus, you can take all these SSE formula and you can say, okay, I have my xi, yi fixed. I know them, it's measured data, and I want to get these parameters a and b to get my line of regression, a plus bx, so that I can draw it, because if I don't know the parameters, I can't draw any line. I don't know how to do that. So to get them, I am minimizing this expression, doing just some partial derivatives, equating them to 0, so on and so forth, and I get these quite ugly looking expressions. But anyway, they work. They work, so you can get these expressions. It's a reminder that you can use many different distances in here. So there are some variations of linear regression. Of course, today we'll be getting in, well, most of this lecture we'll be talking about linear regression with SSE, so sum of squared errors and distances we are calculating like in Euclidean space. But of course, there are many special cases, and you may see in some articles or in some works, you can see some different methods to calculate that distances. So here is an example, like something like LP distances. Okay. Here is some more visual example for you. This is the case when we are trying to perform regression of few points. Here are 3 points that are basically randomly chosen. You see a blue line. That's a true line of regression. So that's what you get when you calculate with all these formulas that we have. And here is a green line. I can move that around. I can move this line. I can change its position basically as I want. And what I want you to see, please pay attention to the plot on the right. Here, here you see our, let's call it, error function. So our error function is, that's basically, I'm calculating that SSE, and you might see here these points. The green point corresponds to this green line. So I'm taking parameters of this line, I'm plugging into all that formulae, and at the end of the day, I get some value for the error, for the SSE. And I am putting this point here. Here is the real minimum of that function. So our minimization method is basically trying to get to that true minimum by changing parameters of the line. So if you are solving this problem with some sort of minimization method, and in case of many parameters, many points, and so on, that's really preferable to use some sort of minimization, because these analytic expressions, in most cases, you will have some troubles with them. So probably you may want to employ some numeric methods. You will be basically minimizing something like this. How do you think? What is this function?
Average error.
Yes, but how it looks like in 3D, for example? Any ideas?
Like parabola, but
Yes.
in
Yes, absolutely correct. That's a paraboloid. Here we, well, here is just some sort of part of it, but you may probably believe me that if you make this picture a bit bigger, you will have some sort of parabola in 3D. And how do you think if I add more points? Like a tricky question for you. I will add more points. Will we get here more dimensions in this picture?
no.
No, because we're working in the space of parameters and we only have 2 parameters.
Yes, absolutely correct. This is the space of parameters. So the number of dimensions you have here is equal to the number of parameters that we have. Here I have added some more points, and now you can see in 3D it looks more and more like paraboloid. Of course, the more points I add, the more spiky it can get. So the more clearly we will see what is this function. And once again, when I'm moving around this line, I'm trying to get somewhere near the minimum. And when I'm getting to that minimum, I will get my parameters for the regression. So that's what we have. Here is one more approach, not getting deeply into that formulae, but what I want you to know, if you take that expressions that we had previously from the calculus, you can note that some of them can be, let's say, rewritten in terms of statistics. So we have already considered statistics with you, and now you can see that these parameters, that A and B, can be described in terms of some functions from statistics. For example, like mean value or some uncorrected or biased sample standard deviation, and so on. Covariation, you can call it. And here are these expressions. So expression for A looks quite simple. Expression for B looks a little bit more complicated. But here is an interesting thing. When we are talking about that B coefficient, you see the expression here. So it contains rho. Rho is a correction coefficient, or so-called Pearson correlation coefficient. So we were talking about correlation, and hopefully you remember all the things. And here you see this correlation in the expression for coefficients of linear regression. And this is the reason why regression is called regression. So this is sort of interesting reason, this rho coefficient. What it makes, here you see some points scattered. I can draw a line, so-called SD line, so standard deviation line. That's the line that I get if I don't have this rho. So I'm just drawing the line that has all these sigma y divided by sigma x coefficient. And when I'm doing the exact regression, I'm getting this rho, and this makes my line a little bit more horizontal. That makes me that makes it a little bit more horizontal. And that basically means that your data is let's put it in words of Sir Francis Galton, who has discovered that in some sense, regresses towards mediocrity. So you have some sort of mean value, and your line has some slight tendency to get a little bit more to that mean value. You can check this this resource. You can read his original article about hereditary of hate in people and how tall is someone. So you can check that. But the idea was that if you have some sort of, I don't know, you're getting some result, and this result has some sort of systematic something systematic in it, and it has some part of luck. So for example, I don't know, someone is winning a game, and this is some sort of result, and this is result of efforts of the players, and plus some sort of luck. And if you are collecting some statistics, you will see that if you are, I don't know, checking the next game and the next game, you will see some sort of tendency to the mean value, because all that luck parts, they are some sort of evening, and you get only the result that does not depend on any chances. Maybe a bit of convoluted example. Let's put it another way. So for example, suppose I gave you some sort of test, and I put in there some questions that, I don't know, you definitely don't know answers to that. I don't know, some sort of biochemical questions or whatever, so something like that. I'm giving that test to you, and you are trying to answer that test. You have, I don't know, 4 choices for every question, and you are trying to make some sense of it. And probably, if there's a large enough number of people taking that test, we will always get some very good scores. I don't know, someone will solve all the problems, and we will get some low scores. So somebody solved none of the problems. But now suppose I have chosen the people that scored high, for example, from 90 to 100, and I give them another test. What will I get as the result?
Probably same distribution, but in
Yes.
smaller scale.
Yes, absolutely correct. I will get the same distribution. So once again, someone will fail all questions, someone will answer all questions, and so on. So what happened? They have regressed towards the mean value. So there is some sort of mean value. If you are randomly choosing answer to the question, you will get, for example, something approximately 25% correctly. So 25 points out of 100 you can get by just luck. If you don't know how to answer any questions, it doesn't matter how did you score on the first test. So you might get 100 points, you might get 0 points. If I will give you another test with the same setup, you will get something more closer to 25. So you are some sort of regressing towards that mean value. And that's the reason behind this name, regression. So it regresses. And here is the quotient row that shows you how much it regresses. Okay, so one more small question about this formula. Once again, that's the previous formula just rewritten in terms of statistics. Looking at it, you can tell me one interesting thing. At least you can name me at least one point that regression line certainly passes through that point. What is that point?
Mean value of x
Yes,
and y?
absolutely correct. X and y. If x is equal to mean value of x, y is equal to mean value of y, you get zeros on both sides of this equation. And of course, 0 is equal to 0. So please remember, regression line always passes through the center of mass, if you wish. Okay, here is one more demo for you. That's a point cloud with some adjustable parameters. I will draw some random samples from normal distribution. You see sigmas of this distribution. I am trying to change them. And please note how this line passes and where are these squares. So these squares, they are showing to you some sort of principal directions. In a coordinate system that will have them like x and y, you will get that matrix in the Gaussian distribution, you will get the diagonal sigma matrix. So if I wish to draw a line of standard deviations, I will draw starting, for example, from this point through the center and somewhere out there. So that will be my line of standard deviations. Now look how the regression line goes. And here is a question for you. Why does it go this way? So what is the reason behind that?
It kind of regressed, as you say.
Yes, it regressed.
Because of correlation.
Yes, because of correlation coefficient rho. That correlation coefficient rho that intermingles into that B coefficient that I showed you before and that we keep track in our formulae, it makes what? It is multiplied by basically parameter of the standard deviation line. It's always from, its modulus is always from 0 to 1. So it makes it smaller. So it makes your line to look more like constant function. And the smaller is correlation coefficient, the closer this line will be to what?
To x-axis.
Yes, to horizontal line. So if I'm making this a little bit more round, I get my correlation coefficient smaller. So you remember that from the previous lecture. And when I get it smaller, my line tends to be more horizontal. If I make this, let's say, this way, I have a large coefficient of correlation, and as a result, my line almost coincides with the line of standard deviations. So hopefully that's intuitive for you. Okay, coefficient of determination. I told you before that we need to have, for each method of machine learning, we need to have some, let's say, tool to measure how good is it. And this coefficient of determination will be our tool to express in numbers how good our regression was performed. So here you see once again some data sets. So these are some random points, or let's say some measured points. Here is my regression line. So that's the model I have. And coefficient of determination, these R squared, is basically the variation in data that I had, the variation in data, minus the variation of residues divided by the variation of data. So you can see here all these parameters. So like I'm taking all these points, I'm projecting them to the y-axis. Once again, I remind you that x and y axes are not symmetric in our problem, because x is a feature, y is a class label, so they are not symmetric, and performing some operations on y-axis have no meaning on x-axis and vice versa. So doing something with x-axis might have no meaning with y-axis, because they have different nature. So projecting everything to y-axis, I can see that I have some sort of variation in data. I'm drawing my regression line, and I see that, of course, my regression has some sort of variation. It predicts all these points. So these red points, they are predicted by my model. I'm taking the same x, I'm trying to calculate the y value, and I get a point that lies, of course, on the line, because that's my model. So I get some variation in there. And of course, I can calculate so-called residues. So how much my prediction differs from what I have actually measured. And that gives me some sort of residues. And these residues, of course, they have their own variation. So I can calculate all these things. And this is what I have. And this is called the fraction of the data variance explained. So I have some variance in the initial data, and I say that some part of this variance can be explained by the fitted model. So what I'm basically saying that in these data, I have some sort of pattern that I suppose is described with a linear function, and there is some sort of randomness to that. And I'm saying with this linear pattern, I can explain, for example, 90% of the variation in my measured data. All the rest, I don't know, maybe there is more to that model, or it's some sort of randomness, and so on and so forth. Of course, there is this quantity like FVU is fraction of variance unexplained. That's 1 minus R squared. Okay, so some sort of conjugated parameter. So what we want, of course, we want our R squared to be as big as possible, and the biggest value we can get is what?
Mean, or no?
Think about even its name, the percent of explained variance. It's just 1. So the biggest value you can get is 1. The lowest, of course, is 0. Yes, because it's just some sort of fraction. what are fractions? It's some parts of 1. So you can get 0.5, 0.9. If everything is perfect, maybe you will get 1. But of course, you can get more than that. R squared? No, I don't think you can get... maybe, yeah. I don't think that you can make that negative. Okay, so here is some sort of derivation. Not getting into that. I don't think that we have time for that. But if you want, you can check these formulae that derives the expression for R squared. How do you calculate that? So on and so forth. And maybe the most interesting part is this one. So you can, performing all that calculations, you can show that the variation in data is always equal to the variation of the regression plus the variation of residues. It's not so complicated, it's just a little bit tedious to get that, but hopefully you will believe me that this is the case. So these variations are you can describe them with this form of equation. So variation of data equals to variation of residues plus variation of regression. Of course, you can write that in terms of sigmas, and you have something like like triangle equality for right triangles. I guess Pythagoras theorem. So you have square of sigma data is equal to sum of squares of sigma regression and sigma residues. So this is a crucial part, let's say. Okay, here is a geometric interpretation of all that things. So you remember all that squares and points from the beginning of the lecture. And so here you have a little bit more like images. This shows you variation in data. So we have some mean value in data, and we are calculating all that squares just by calculating these distances to that to that data. Here is the variation of residues. So I have my regression line, and these are basically errors that my model is doing. And this is variation of regression. So these blue points, these are predicted points. So I have a line of regression. I'm predicting these points. And here are basically squares. This area of these squares represents that sort of variations that we all add up, and we get this thing. Okay, and you can prove that this formula, like variation of residues and regression, is equal to the variation in data. Well, and that basically has some meaning, because otherwise will we be able to speak about some sort of percent of explained variation if we were not sure how much we have, well, total variation. Okay, adjusted coefficient of determination. Not getting into that, just few words. If we are trying to compare regressions with different numbers of features, so like we are increasing the number of dimensions in our space, we will always get better and better R squared. So just by adding some more and more dimensions. And of course, it's not good. And you may probably guess why it's not good. So just from the practical point of view. How do you think?
Probably correlation will be less coefficient of correlation will be less because will be more randomness and more. Oh, I don't know.
It creates me some troubles if I'm trying to compare different models. So first of all, that creates me some troubles. So if my R squared gets better and better every time I add some new dimensions, without any respect to the data that I'm putting into that dimensions, I can just put some sort of garbage into there, and that model will look better than a different model that doesn't use any garbage. And that's no good. So it impairs my ability to tell which one is better. I don't want that. If I'm doing some machine learning, I would like to see that my model gets better when it really gets better. If I'm adding some garbage data, that will be perfectly okay, and I will even want that if my model will get worse. So I can understand that this is some sort of garbage data. It has nothing to do with the problem I'm solving, and I just remove that features from the consideration. That will be okay. I will want my model to get better when I'm adding some sort of relevant features. So I want my features to be relevant, to get some relevant results. And if all this machinery is tailored that way that if you add some new dimensions, you always get better, it's no good. So I'm considering, I don't know, I'm considering some problem and I'm adding some new feature, whether it was raining that day or not. If my problem has nothing to do with some sort of weather forecast, so probably it's not a relevant feature and I don't want that in my data set. But formal expressions will show me that everything became a little bit better, I have a better regression. No, it's no good. That's why we have some sort of adjusted coefficient of determination that takes into account the size of the sample and number of independent variables that you have in the regression equation. And that is some sort of, it tries to compensate for that problem for what you get by adding some new dimensions and make your models better comparable, so that you can compare models with some features and without them. So in short, these adjusted R square, it prevents you from overfitting, because you are just overfitting when you are adding some new features without any consideration, do they have any meaning or not. Okay, here is some example. Once again, not getting into that, just a calculation of a regression line on 3 points. So you have 3 points, you have coordinates for x's and y's. These are the 3 points, 1, 1, 2, 4, 4, 5. You calculate mean values, you calculate sigmas, you calculate rho, put everything into that formulae, and you get your expression for the regression line. So nothing complicated here. And you can calculate R squared and get the percent of variance explained. In this case, it's 80%. So your model is, let's say, so-so. So it explains data. Here is an example in Python. You see that sklearn has a linear model, and from this linear model, you can import linear regression. And you are asking to fit these data of x's and y's with this model, and you can get some numbers out of there. Please note this parameter fit intercept. That means whether you are fitting a true linear model or you are fitting, let's say, an affine model. So that basically tells you whether you have that free parameter at the end. If you are fitting just some sort of a times x, that's a pure linear model, and this means that fit intercept is false. If you are fitting something like a times x plus b, this means that you have some sort of intercept. It's that parameter plus b. So if you want that, you should put this parameter to be true. And here how you get parameters out of there. So intercept leaves separately, you can get that, and slope, you can get many different coefficients because you can do in multiple dimensions this regression, so you can get them with KF function. And here I'm calculating the coefficient of the determination R squared. Here we have it. Okay, one more example how to do that in Python. Once again, not getting deeply into that, it's really simple. You see that we have some sort of line, and you see these points are somewhere in the vicinity of that line, so it's probably okay. Here R squared is equal to 0.979. So it's very close to 1, but you see that even being close to 1, it doesn't mean that all points are just lying on that line. No, they don't. They are scattered somewhere around this line. Okay, here is a demo, interactive example with simple linear regression. So hopefully that will start smoothly. And I will show you how linear regression works in sklearn. This is just an example for you to play around, to put some points in here, and you can ask do regression. This demo uses sklearn linear model, linear regression. So that's linear regression from the libraries, and you see the result these libraries give to you. What I want you to show with this demo, let's make once again a little bit tricky question. So we had our loss function in form of SSE. So we had some sort of errors, distances between these points and line. We have squared them, we have added them, so on and so forth. And you remember the form of that function. It was some sort of parabola, yeah, in many dimensions. So here we have two parameters, so in two dimensions, and the third for the value of the function. Okay, so that's what we have. Now I'm asking you a tricky question. What will happen if I'm taking some point and I'm making an outlier from that point? Can you predict the consequences of getting one outlier into our linear regression? And why it will happen that way?
Probably it will slightly tend to that point.
Okay, so you
Because
think it will slightly tend to that point?
The model will try to fit to the data point and consider it as equally important as all the other ones. So our line will be somewhere in between this quote-unquote line of points and that one outlier.
we have squared, right? So squared difference will like have big influence on line.
Yes, yes. So you all are absolutely correct. We will have really big changes in the slope of the line because our function, our SSE, well, you see now what happens. So what happens to the line? Because SSE contains squares, and the square function grows very rapidly. So when I'm getting an outlier, it's adding an enormous amount to that SSE. Of course, our methods try to compensate for that, and it basically starts disregarding the rest points, trying to make something with this one outlier. So that's the thing I want you to be aware of. So outliers can make a real mess of your linear regression. So if you are using some linear regression from all that sklearn, so on and so forth, you will probably want to do something with outliers. You may want, I don't know, you may want to try to get rid of them or do something else, but you should be really warned that if they get into your data set and you just simply put that into linear regression, you can get just some mess of it. So as you see, this line tends nothing like like these points. Of course, we don't want that. Of course, there are some methods to do something with that. For example, I don't know, maybe you will want to check method like ransack. So the idea is taking some subsample of your points, taking it randomly, and if there are not too much outliers in your data set, you will be probably getting with much higher probability some, let's call them normal points, that are from the main, that contain the main tendency of your data set, but you will not get the outliers. So one of the methods. Or you may try to do something different. So there are, let's say, different methods, but the main thing is to be aware of the problem that we have. So yes, we have a problem. Outliers can mess up the whole regression. So please be careful with that. And you understand, of course, the reason why. Because that's the loss function. It just grows too rapidly on these deltas. Okay, polylinear regression. So before this part, we were talking about linear regression and basically with one feature. So we had an X, we had Y, and we were just doing something with that. Now we are getting into a multi-dimensional space. Because we are thinking, well, one feature is a little bit too little. So we want more features, and we want to be able to work with some more complicated data sets. And here is an example. How do we do that? How do we treat all that things? It's really convenient in case of multidimensional spaces to turn our notation to some sort of vectors and so on. So we would like to rewrite our formulae in some sort of vector representation. And here is an example for you. How do we do that? So here will be my model Y. And I get some input features like x1 to xn. And this model will basically be what? So that will be some coefficients that I'm multiplying by each of the feature. I'm adding everything up. Maybe I add some sort of intercept or this A, and that will be my result. That will be prediction of my model. Once again, please remember from the previous lecture, we have different types of features, and not every feature that you can express as a number can be multiplied by something or can be added or so on and so forth. So in some cases, you may want to be careful with that and not just put everything in one bunch into the linear regression and expect something good out of that. So maybe some features, they don't even have such a meaning that you can multiply them by numbers or you can add them up. So that may be the case. Okay, and here is the vector expression for that. So this part you can easily express like some sort of vector of parameters, B in this case, that is dotted. So you have a scalar multiplication with the vector x, so vector of features. And when we are multiplying that, we are getting this part. And here is just some sort of A that we are adding to that. Of course, you can equip your vector of features with some sort of constant feature that contains that one, and you can forget about this A times 1. You will just incorporate that into parameters B. So that's pretty okay. Okay, so what do I have here? So here is an example of when we are doing some sort of Python. I'm trying to fit some features and get results out of there. Once again, I get my intercept and I get slope B, but this time we have more numbers because I'm working in a multi-dimensional space. You see, these numbers are very close to how did I generate this sort of data. So I was doing basically this hyperplane with some sort of randomness added to it, and so the hyperplane was perfectly recovered. Okay, how do we solve that? There are many ways to look at the polylinear regression, and I will try to guide you through some of them, maybe without some sort of too much details. Let's see how that works. Okay. So first of all, what do I do? To make our calculations a little bit simpler, consider that we have among our features, we have a constant feature that is always equal to 1, and that is incorporated in our vector of features. So this xi, that's my data point. So that's basically a collection of features that I get when I performed one measurement of something. So this x1 ith to xn ith, it's what I have measured, and this 1 is just a constant 1. Okay, and I have my measurements. These are y's. So this is the vector of y's of my measurements.
So y's have the size of n, and x's have size of n plus 1.
You see, it's a little bit more interesting. This big N, so a capital N here, it means the number of measurements. So basically the size of my data set. So in my data set, I have 100, 1000 measurements, and so on. Each of these y's corresponds to one measurement. I have measured once, I have one number. These x's, they are a little bit more tricky. This I in brackets, that is basically the number of the experiment I am performing. So y1, this just one number, corresponds to the whole vector x with 1 in these brackets. So that the whole vector corresponds to one measurement.
Okay.
So this n, this small n, is basically the number of features that I have. Let me maybe think how do I put that a little bit more simple. So you have, for example, two devices. Well, maybe I'll try to draw that. Okay, so what do we have right now? So for example, suppose you have, I don't know, two devices that are basically measuring something. So you have device 1, you have device 2, and these will be my features. So whatever they measure, they give me some sort of numbers. That will be my features. And I'm trying to predict something with my model. So for example, whatever these devices measure, I want to predict linearly, for example, some sort of, I don't know, some temperature, for example, of something. So it doesn't really matter so what I do, but these are. So this will be part of my x. So if I'm measuring, for example, the first time, I'm doing what? I'm doing some experiment. So I'm measuring x. So I'm measuring x1, and this is a vector. So this is a vector. So I have measured some number here, for example, 1 and 2.5 in here. I'm measuring once again. I'm doing experiment number 2, and I'm getting, for example, here 2, here 3.5, and so on. And now I'm trying to do, so I'm collecting a data set. So these are my x. Now I'm trying to measure my y. That will be basically the class that I have. So for example, I'm predicting some sort of temperature. This is my y. I will measure y1. For example, I don't know, 50. This is y1. I will measure here, I will have 60, for example. This is y2. y1 and y2 are just numbers, just plain numbers. Now, when I'm collecting everything that into a data set, I will collect these numbers like this way, and I will make y vector from here. So the number of components in y vector will be equal to the number of measurements I have performed. Let me write one more to make different number. For example, here will be x3, let's say 1.5, 2. Let's say 7, and let's add here, I don't know, 55. So now you see that the number of components in X's and in Y, they are different. Because here I have collected X's like this way, and they are equal to the number of measurements, to the number of the devices I had with which I want to predict something. And Y I have collected like this way, and the number of components in Y vector is equal to the number of measurements I have performed. In general case, of course, you will get more measurements than you have features. Otherwise, it's a little bit strange problem, let's say, this way. So in general case, you will have much more components in Y than you have in all these X's. Of course, now you will ask me, how does it work? Yeah, because we have different number of components in X's and Y's. And what should I do to like connect them? How do you think?
Some systems of linear equations or something like that.
So I should
No.
somehow transform these things into my Y. And it's done the following way. So I'm collecting these vectors. I'm collecting them in some sort of matrix. Because each of these Y's, it's a result, I'm supposing at least, it's a result of something linear. So I'm telling that my Y1 should be equal to what?
Y1, 50? Or what?
I'm predicting.
Oh, some A plus coefficient x1 plus coefficient x1, first value of x1 and plus second value of x1 multiplied by b2 like this.
Okay. Let me do that a little bit more in a way with a little bit more like vector way. So I will add here a constant feature. It is always equal to 1 everywhere. So I do that. Now, what is my model? So I want a linear model. So a linear model means that, yes, I'm taking all the things with some sort of coefficients. But as I told you, I want them to do that in a vector way.
So it's like
yes,
dot product.
Yes, so I will imply a dot product. So I'm taking some vector of parameters, and I'm taking a dot product with x1. And that's my y1. So this vector of parameters, it contains all the free parameters that I have in my model. So that's my model, basically. And you see no indices here in this W. Why?
Because it will be applied to all y's, and it will be a model.
That's my model. It should work on all the input data. It's not an input data, that's a model. So that's why I will have y2 equals to w times x2, and y3 equals to w times x3 and so on. And I can write that even in a more compact way if I collect all these x's into a matrix, into one big matrix. I can take all these x's and collect them like so. So for example, I'm taking all these numbers and I'm putting them in a row in a matrix. So here is one row that contains my x1. Here is another row that contains my x2. Here is another row that contains my x3. Now, what will happen if I multiply that with a vector column that contains me parameters, for example, w?
It will give array of y's.
Yes, absolutely correct. Because we are multiplying row by column. So multiplying this thing by this thing, I get y1. Multiplying this by this, I get y2. And here I get y3. So I'm getting basically a vector of y's. So here is my vector y. And that's the reason behind that. Why do I write these vectors? Well, this way. So I will have my vector y to be equal to matrix of x's times vector of parameters. That's what I have. Okay. Now let's get to some to these equations. Okay, so now I have collected my parameters into this matrix. That's what I have. That was the equation that I wrote for you. But now we are remembering one interesting thing. This data is measured. So when I'm multiplying my matrix of x by the vector of parameters w, I don't get the exact y. I get something approximate. If they were perfectly equal, you will definitely know how to solve that. You will have just some sort of system of linear equations, so nothing very interesting. But this thing is approximate. So you can't get the exact y you have. You get something close to that. And we need to find a way how to make some sense of this sign of approximate equality, what it means to be approximately equal, and of course to get some meaningful result.
We probably can make it equal if we will have same amount of parameters and samples.
Yeah,
no.
maybe yes. For
Okay.
example, you can always draw a line through 2 points. That's okay, but it's not the problem that we want to solve, of course. Because we are trying not just to draw some line, we want to make some sense out of our data. So we are having some data, we see some trends in our data, and we want to fit our line to that data. So we actually want to have more and more samples, because more data we have, it's more probable we get some meaningful result. So what do we do here? How to make sense from this out of this sign? We can think about it this way. So for example, I have these xw. These are predictions of my model. So that's what my model predicts. For each data point, it gives me some number that tells me my model predicts 1 here or 0.5 there, and so on and so forth. And these are y's that were actually measured, that basically I wanted to get in a case of perfect model. So when I'm calculating this difference, these are basically the residues. So how much my model differs from the exact measured values. And if you take a norm squared of this thing, what will you get?
Symmetric matrix. Or... oh no.
No,
It's like square root of eigenvalue of some kind of this.
Oh,
no.
No. You're doing
No,
something.
this
Here we
vector.
have like
Let's
vector
return
minus
to the
vector.
beginning.
So we will
What
have
is
the
this
vector
object?
of dimension n under the norm squared. And
Yes.
I believe it is an L2 norm, so we will have just the sum of squares of the coordinates, and each coordinate is a residual. So we will just receive the same objective functions that we've talked about before.
Yes, absolutely correct. Absolutely. So this object is a vector because y is a vector, and you are multiplying a matrix by a vector, so you get once again a vector, and the difference of vectors is a vector. So this thing, it's a vector. You are taking square of the norm of the vector, so in the Euclidean space, you just have sum of squares of differences in coordinates, which are residues, which returns us to the beginning of this lecture, and we get the same SSE that we had previously. So yes, it is. And you may find, well, if you use some sort of equation, so on and so forth, you do the minimization, you can get the result when this thing is minimal. So this is the equation that you get at the end of the day. I'm not getting through all that mathematics. Moreover, you will need some sort of equalities that are rarely used. I have put a link for you to Matrix Cookbook. Maybe you would like to check that. There are many nice equalities with matrices. Maybe they will help you at some point. But this is the result you have. And you can express W from that. You can express it and get this sort of expression. So x transpose times x to the minus 1 times x transpose times y. And this whole thing is often designated as x plus, is called a pseudo-inverse matrix of x. And that's its basically definition. Okay, how much time do we have?
5 minutes.
5 minutes. Okay, so I will tell you just one thing, and we will make a break. So please note, when we are looking at this matrix, so when we were solving some sort, well, these sort of problems, so that some matrix times some vector equals to some different vector, and we were searching for that vector. So for example, you had an equality x times w equals y. You could think about, if that matrix was good enough, you could have multiplied by x minus 1 and get the result. But this is not the case. There are many reasons to that, but which one is the most, let's say, striking to you?
They could be very big. There could be very big matrices to process.
Well, not exactly. Some more, like say, mathematical reasons. So why do we do that? So
Error, maybe, like
so it's just one of the last points I'm doing at this part. So we had a matrix multiplied by a vector, and it was equal, for example, to some y. So suppose we are solving the equality. If this matrix is good enough, you multiply that by x minus 1, and you get something like w equals to x minus 1 y. But in this case, we can't do that. Let's think for a moment. What should we know about the matrix so that we can say it has an inverse? Do all the matrices have inverses?
It has to have it has to be square, and
yes, it has to be a square at least. At least it has to be square.
The determinant must be not 0.
Yes, and determinant should be not 0. So let's start with even with the first point. Will this matrix be square matrix?
No.
No, of course it will not be.
X
Why should
itself
it ever
won't.
be square matrix? Because along one dimension of the matrix, the number of rows we have, it is equal to the number of measurements we perform. The number of columns we have is equal to the number of features that we measure. Why on earth will be the number of features that we measure be correlated somehow to the number of measurements that we perform? Moreover, it's not good if you have your number of features bigger or equal to the number of measurements. It's no good. Most of the methods will fail in that case. You will probably want, doing some sort of machine learning, whatever method you employ, whatever you do, you will want the number of measurements to be higher than the number of features, at least, I don't know, maybe 5 times or something like that. But you definitely don't want them to be equal or whatever. So the first reason is that matrix X is not square matrix. So how can we talk about any sort of inverse matrix? No, we don't.
And even
that
here in the
doesn't work.
formula, like we do have X transpose times X. So this will be a quadratic matrix. Okay. Even if it will be having a normal, like a determinant non-zero, okay, it might be fine. But in the end, this matrix X transpose times X can be, I believe in English, it is called ill-conditioned. So like the ratio between the biggest eigenvalue and the smallest eigenvalue will be big. So it's a conditional number of a matrix. And this will imply that this matrix will be very, like we will be able to like physically take an inverse of it. But the result of taking the inverse will be with many errors, computational
Yes.
errors, arithmetical errors. And even though we do have like a good matrix theoretically, in practice, it just won't work for us because the errors while taking the inverse will be too massive for us to compensate them in any other way as further on.
Yes, that's a very good point. That's a very good point. And yes, in practice, in most cases, we retreat to some sort of numeric minimization methods and do not calculate all the things with inverse matrices and so on. So yes, you are perfectly correct that way, and that's really the reason why we employ some sort of minimization methods instead of calculating that in, let's say, a nice analytical way that we can. But anyway, I want you to know about these pseudo-inverse. And yes, you are absolutely correct that this matrix is quite good when we are multiplying X transpose by X. Moreover, I will tell you, it's not only a quadratic matrix. That's easy to see. That's easy. If you don't have features that are linearly dependent, this matrix will have an inverse. If you don't have features that are linearly dependent, that will be a pretty good matrix, I should tell you. I think I won't prove that. You can think on your own why is that way. That basically comes up from the idea that if your matrix has a zero determinant, there should be at least one vector X that is mapped by that matrix to a zero. And that's why you can show that if this matrix has a zero determinant, if that happens, there should exist some sort of X that it maps to zero. So you can write that this way. So X transpose.
Can this matrix be called Gram matrix also?
I'm not sure, actually. I know the whole construction when you have all these transposes with inverse and so on is called pseudo-inverse or Penrose matrix. But I'm not sure about the separate matrix of X transpose X. I should check that on my own. So here are just some sort of few lines. So here you have X transpose X if it had zero determinant, you should be able to find some sort of x like this to get vector 0. You can, in this case, you can multiply that by the same x transposed that removes you this vector. Then you can write it like this one. So you have x. Sorry, I didn't hear. Okay. X here transposed, and you see that this is some sort of vector, and this is the same vector transposed. So this means that x times x equals to 0. So if determinant x transpose x equals to 0, you can show that then x times some x is equal to 0 as well. And this may be the case only if you have in your X matrix, if you have some linearly dependent columns. So you should be aware of this thing as well. It means when you are doing some sort of linear regression, that's really no good if you have some linearly dependent features. So you may want to get rid of the features that are linearly dependent. That brings you some troubles. So from the analytical point of view, you see that your formulae, they stop working. And if you do that numeric way, the closer some sort of columns from this matrix are to being linearly dependent, the more troubles you have when calculating. So your numbers are getting not good, let's say. Okay. So with that being said, let's probably make a small break, I guess, and then we will return and consider the rest things I have for you. Okay, so a break. Okay, so let's continue. Before we start, a small comment that I have missed myself this point. When we are calculating R squared, I showed you a theorem about the sum of variances, and basically we will use that in here just in a moment. But what I want to point out that if I am doing some sort of machine learning, I'm using that sklearn, so on, I have fitted some data, and on that fitted data, I will always get my R squared from 0 to 1. That's okay. But if I'll try to recalculate that coefficient on my some sort of separate validation set, it may happen that yes, it will get even to negative values. That really can happen. But the trick is that you use different data sets for, let's say, calculating R squared and for fitting your model. So that theorem about the sum of variances, it holds only when we are working with some sort of fixed set of data points. If I am training my model on one set of data points, and then I am calculating R squared on some very different set of data points, I can get very strange results. So yes, that may happen. Yeah, of course, it's like I'm missing this point just because when we are proving that theorems for R squared, we are fixing our set of data points and we are working with them. So it looks a bit strange to calculate it on something else, but in practice, you will exactly do that. So yes, in practice, you might stumble upon some negative R squares, but just because of this reason. So you are using a very different validation set from your training sets, and it may happen that, yeah, you get something very, very, very strange in that case. Okay. Yes, some comment? No? Okay, so let's return to the linear algebra perspective. And whatever I showed you may be called as some sort of matrix method. So we can, at least formally, we can write the solution to our linear regression problem in form of some matrices and in form of the pseudo-inverse matrix of Penrose. That's great. Now I want you to show some sort of point of view on the linear regression I'm sure you haven't seen previously. So I guess it may be a little bit interesting from some sort of maybe philosophical point of view. So just to look at it from a different angle, a different perspective. So first of all, once again, we are starting with the equation. So x times w equals y. W and y are vectors. X is some sort of matrix. What does it mean? Well, there's an interesting caveat to this thing. When we are calculating x times w, I will get this vector y from so-called column space of the matrix X. Let me draw that on a board. So I want you to feel the thing. Sometimes it gets hard to get rid of everything I wrote here. So maybe okay, I'll let this thing leave. Okay. So suppose I have a matrix X and I am multiplying it with vector W. And now I'll write this matrix X in the form of vector columns. So I will call them, for example, X1, X2, well, and so on up to some Xn. And I'm multiplying that with a vector W that has components W1, W2, Wn. Now, please note, how do we multiply a matrix by a vector? Row by column. So I'm taking this row and I'm multiplying each of these components by the corresponding coefficient here. And I'm putting them into the first slot. Then I'm doing the same thing with the second slot and so on and so forth. But I can write the same thing this way. W1 times vector x1 plus W2 times vector x2 and so on up to Wn times vector xn. Okay, so so hopefully you see what happens. So I'm just rewriting this thing in this form. So you can check that everything works as previously. So I'm multiplying W1 by each component, here W2, so on and so forth. And if I add everything up, I get the vector that I expected. Now, what can you say about this vector? So let's call it some y. This vector is basically a linear combination of vector columns. This means that it always belongs to the some linear subspace that we call a column space, because it's always a linear combination of these columns. These columns, they may span the entire linear space where these vectors live, or may not. How do you think, in our case, will they span the entire space or not? Well, in most interesting practical cases.
Could you repeat, please, the question?
Sorry, didn't hear.
No, I didn't hear. Just I don't know if anyone else.
Okay. Let's think about it this way. So this vector lies in a span. So it's a linear space that you construct.
Yes.
From the vectors x1, x2, up to xn.
Yes, and it won't lie in other axes, other samples, probably.
So what can be the maximal dimension of this thing?
Dimension of x. So number of features.
Dimension of this span, I mean, how do I put that? Well, if we have a three-dimensional space,
max rank, like.
And suppose I'm considering a plane in here. So if I'm describing all vectors in this plane, I'm using like three numbers, but this space itself, it's two-dimensional.
Yes.
So in here I have n vectors.
But they have but how many components they have, those vectors, or this does not matter?
This doesn't matter basically.
Oh.
So maximum you can get from here. Well, you can think that they have many components. So the maximum you can get here is this small n. Yeah, of course, if you have just one component
number
in
of
this
features,
vector, you will get only one dimension. Yeah, so you're right in that sense. But if we have many components in here, so you can maximally achieve small n. That will be some sort of hyperplane in some higher dimensional space. And the thing is as follows. This number is basically number of features. The number of components in these vectors, it's the number of measurements you have performed. So in practically interesting cases, the number of measurements should be much higher than the number of features. So these vectors are living in some very highly dimensional space, but they are basically spanning only a small dimensional, at maximum small n dimensional subspace of that. So that's what we get. So this is the column space. It just spans some part of that bigger space. And now let's check where it leads us. So all in all, I think I will not go through all this math. So maybe you can check that on your own. But we can show that in this space we have this sort of very interesting operator. So x times x transpose x to minus 1 times x transpose, and this is a projection operator that projects our vectors to that column space, to the column space of the matrix X. So I'm not proving that. Here is basically the proof, but I'm not doing that. What I want to do, I want to show you the connection of this thing with the linear regression. Let's think it this way. So what do we have in here? So we have a matrix X where we have put all our measurements, and we say that if our model is, well, and we are multiplying this matrix with some sort of vector with parameters to get our prediction. The prediction we get always lies in the column space. So that's some sort of subspace of that entire space that we have. So that column subspace is some sort of hyperplane. And whatever we calculate will lie there. Now I'm asking you a question. Where does vector y lie? The vector that we have measured, that we are expecting to get. Does it lie in the column
this
space?
subspace of span x1, xn small?
It's measured vector. It has no obligation to lie there.
So we're
you see,
constructing such a subspace to include that vector.
No, so probably it could be in some other space, but we can project it on our measured model.
Yeah, that's a really good idea. So it lives in an ambient space. So we have all that measurements. So let me return to the whiteboard and let me reiterate once again. So that's a really, really nice idea. So here is my ambient space. The number of dimensions of that ambient space is equal to the number of measurements that I have. So if I am trying, so I have, this is my y, let's call it model. So I give letter M here, and I have some sort of y that was truly measured. And this y of truly measured has the number of components that is equal to the number of measurements. So it lives in this ambient space. Now I have a matrix, I have collected to this matrix all my measurements of my features. Its dimensions are number of measurements, let's call them capital N, and number of features, we call that small n. When I am multiplying that by any vector of parameters, so any models, any linear model I take, I will always get predictions that, yes, of course, their number of components is equal to the number of components of the ambient space, they live there, but additionally to that, they live in the column space. So there is some sort of hyperplane in here, and all my predictions live in this hyperplane. And there's nothing I can do with that. There's nothing I can do with that because this matrix is fixed. I have measured this. This is my data set. I don't want to change my data set. It is what it is. I can change only these parameters, just looking for the model. But whatever I take them, I always get this thing, and it always lives in this hyperplane. While the y vector that is measured, it is not bounded to my model. Who said that this model is even correct? I'm just guessing it. It lives somewhere where it wants to live. It lives in the ambient space. And now you said a very, very right and correct thing. I want in here, find some other y, some y predicted that is as close to the real y as possible. So the closest I can get. And it turns out that the closest I can get in here is the projection of this y to this subspace. Why? Because in Euclidean space, if we measure distance between vectors, and we have shown that we are interested in minimization of a function that is basically difference between vectors, norm squared, so on and so on. Well, the minimum will be basically distance along the perpendicular to this hyperplane. And that's what we get when we project this vector. So at the end of the day, what we have, so linear regression, in some sense, it incorporates inside of it some sort of projection to the column space of the matrix that you have created from your measurements. So here it is. Okay, so here are some small pictures that show that to you. So here is the projection. Here is the projection. Here you have that y perpendicular, the subspace, I mean the column space, and so on. What is interesting here that you can make sense of that r squared if you look at this picture. So here is my observed y, here is my fitted y, here you have residuals, and if you build this sort of right triangle, you may know that if we have that constant feature in our y, there is always a vector that is equal to the mean value of y times some vectors that contains only ones. It always lives in the column space. Here it is, and you can build the right triangle this way. This angle theta that you see here, the cosine of this angle theta, that will be our r squared. Of course, once again, I remind you that I'm using the same points that I used to get the fitted y for calculating that r squared. Otherwise, of course, you can get something very different. But in this case, it's equal to the cosine of that angle. Okay, here's an example to how to get this with the gradient descent method. Hopefully you know that. Here is some sort of visualization, how it descends to get you to that minimum. That's everything is pretty simple. Yes, a big warning for you. So gradient descent is definitely not the best choice of minimization algorithm. And you probably saw why in the lecture on the optimization. So here I use it just for the purpose of demonstration. So it's just a very simple method. So you can get through this formula and understand how it works. If you want to get a little bit deeper. But if you do that in practice, if you need to perform such a minimization in practice, please use some of more, let's say, industrial methods of minimization. For example, here I'm using Newton conjugated gradient method, and you see that just in a few steps, it is able to get to the point of the minimum, and it performs that quite quickly. While the gradient, just simple gradient descent, it may stuck even with such as simple functions as as parabolas. Okay. So once more regarding all that methods, you have already told me, and that's really true, that we can do everything with some sort of analytical methods, or we can do that with numerical methods. And everything has its pluses or minuses to that. So some numerical methods, they will need some sort of tuning. Maybe you will need to choose some learning rate or or something like that, but they work well with a large number of dimensions, and they have a little bit less problems with some sort of small values, small numbers. While normal equation, or that equations with all that access transpose and so on and so forth, they don't need that tunable parameters. You have just the exact analytical expression for what you want to get. But they are really slow if the number of dimensions is very large, or number of your measurements is very large. It's really hard to compute x transpose x to the -1. It may be very slow, and it may be even that x transpose x is, let's say, not very invertible. So you have a very small determinant, and you may have some problems with that. They are solved in some sense if you are regularizing these problems. So you can add some small lambda times the matrix, the unitary matrix. I mean the unit matrix that contains ones along its diagonal. So it may be. And of course, you can improve this method with the help of SVD decomposition, but once again, there may be some troubles. So, okay. So we saw different methods of linear regression and how it's done here and there. But now let's do some more, let's say, some more general thing. Let's talk about regression for any basis. You may have thought that linear regression is called linear because we always get some sort of lines, planes, and so on. But it's not. It's called that way for a bit different reason. Can you guess what is the reason?
We don't have some polyline, no, like cubic equations like polynomials and so on. And
why do we
linear
it is called
coefficients.
linear regression because the parameters are linear in the model. We don't
so
have like W1 squared or whatever.
So whatever we get from our model is some sort of linear combination of the basis functions. So that's why it's called linear regression, yeah? So we have chosen some sort of basis functions, and we do a linear combination of that functions, and that's why it's called linear regression. It's not because we get lines and planes. We can get something very different from the linear regression, from line and from plane. And I will show that to you just right now. So here is a very simple idea that gives us large consequences. For example, what we have done before, we were just taking bare features. So whatever we have measured, that numbers, and we just tried to combine them in some sort of linear fashion. But what if you think about it this way? Why do I use bare features? So I'm getting some data point. There are some features in there. But why I'm using this vector as it is? What if I calculate some sort of function on this vector and get some very different vector from there? And only then I will apply my linear regression to that vector I have calculated on that. So it basically means that I have performed calculation of some basis functions on that vectors, and I am now combining that basis functions to get my result. This idea is very simple, but where does it get us to? Let's consider it this way. So I have these functions phi. This function takes vector and it gives us vector in the result. I can perform everything I did before. Just in this case, instead of matrix X with bare features, I will get some matrix of capital phi that contains results of calculating all that component functions, phi 1 to phi n, from my vectors. and some constant feature to make things a little bit simpler. I can do everything I did before, and I will still get something that is basically a linear regression. The other idea I want you to be aware of, you may take any number of these functions phi as you wish. They do not depend on the dimensionality of the initial space your data points were living in. So you can take any number of that. And here is a very simple example. Let me take my basis functions as x, x squared, and x cubed, and perform a linear regression on that. The resulting models I will get, they will look like some w0 plus w1 times x plus w2 times x squared plus w3 times x cubed. We still have a linear regression, but the lines that we will get from these linear regressions, they will look like cubics. It's not straight lines anymore. It's not even parabolas, it's cubics. So this way, you can basically fit with linear regression any polynomial. They are often wrongly called like polynomial regressions. No, they are not. It's still plain old linear regression. What you have exactly done, you have transformed your initial features into some different space with the help of some sort of basis functions that you chose. If you chose your basis functions as x, x squared, x cubed, and so on and so forth, you will get some sort of polynomial at the end of the day. If you choose them differently, for example, I don't know, some sines and cosines, you can get something that looks like some part of Fourier series or whatever. So you can do that, and that's pretty okay. And here is an example in Python that I really like because it underlines how that works in some sort of practical fashion. Please take a look at this. I'm doing a model with a make pipeline. And in this pipeline, I'm using a function, polynomial features, that transforms me my access to that other space with the help of the basis functions. And I'm using on that basis, on that result, I'm using the same linear regression I have used previously. And what I get at the end of the day is the ability to fit, for example, some sort of parabola. So here I'm putting some points. I'm asking, do regression, and I have a parabola. But it's still a linear regression. So please note these two ideas, let's say, or maybe one idea. I don't know how do you count them. But the main thing is that you can use not only like bare features that you have from your measurements, but you can apply some functions to them. You can get into very different space with the help of that basis functions, and then only then you will combine that functions in some linear manner to get the result. And here are some sort of examples how you do that with a different some sort of different functions. Here I'm even doing that with Gaussian basis functions. So I'm using different Gaussians with different, let's say, mean values, and I'm just adding them with different coefficients. And once again, I get something like this. So I'm trying somehow to get this line through the points, but it's still a linear regression. Okay. So hopefully that's more or less clear. Now, now let's get to, I think it's the last topic for today, to the regularization. So in previous lectures, we saw that models that we are building may have different problems. And one of the problems was so-called overfitting. And this overfitting, it's really a complicated problem in the sense that you don't see any troubles when you are doing something on your train set. but you start getting some very strange results when you get to your validation set. So it's not so easy even to catch this problem. You need at least to get your training to the end, and only then, if you have a trained model, you are trying to assess somehow the quality of your model, and only then you see, well, something bad is happening, so something went wrong. And the method of regularization was one of the methods that I mentioned for you that is good to, let's say, alleviate the problem of overfitting, or maybe even get rid of the overfitting of the model. Let's first say it in some sort of hand-waving way. So first of all, when the model is overfitting, what does it mean?
High variance, low bias.
Yes, so we have high variance. High variance means that we have maybe too many parameters in our model. So we want somehow to change and to solve this problem. We want somehow to change or this number of the parameters, so to get to some maybe simpler model or something like that. Or we may try to set some boundaries to the parameters, and with this way to make our model a little bit more restricted. So we want to restrict our model somehow, and we expect that this restriction will make the variability of the models that we get smaller, and that will make our variance smaller, and maybe we will get from that overfit, so we will do something better. And the regularization is the method of to restrict the parameters that we have in our model. And I will show you how that works in case of linear regression. Well, because it's easy to see in this case. But of course, you can use regularization in many, many different models, and probably you will do that even with some sort of neural networks and so on and so forth. But I guess the easiest case to look at it is linear regression, and let's look at it. Okay, so here is an example of overfitting. So you might guess that these points, when I'm predicting them, I would like to predict something like, I don't know, something that looks like sine or cosine, something like that. But my prediction, it passes through all the points, it perfectly passes through them, but it doesn't look like a really good prediction. So probably you might guess that. And now I'm trying to think, okay, this is a bad prediction. How can I get any idea that it is bad? I mean, when I'm working in the small dimensional space, so like in here, I can draw some plots, I can look at them, and I can say, yeah, I see that here something went wrong, so on and so forth. But when I will get to some more complicated data, I will do that in a many, many dimensional space. I will have no ability to draw all these plots, and I need some numerical way to understand that something went wrong. And the first guess, I'm trying, for example, to plot the coefficients that I have in my linear model. So here is the plot of that coefficients. And I'm trying to make sense of that, so I know this is the case when something went wrong. I'm looking at this plot of the coefficients, and I'm thinking, okay, what can I say about them? So what's so special about these coefficients that may hint that something went wrong when I performed the fitting?
They have high variance, and
they are very large.
Very big and very big.
Yeah, so you see they are very, very large. So up to, I don't know, how much is this? 500,000 and minus 500,000. And you see they are changing their signs to plus or minus. Well, you might guess why that happens. Yeah, because if my model has so large coefficients, when it passes through one point, and this model is very, very different from what exactly happened there, to get through the next point, I need to very quickly correct this line,
Compensated.
I need to change its direction. So I'm taking the next coefficient with some very large negative value, but then the next point comes and I should get once again up, and I'm getting the next coefficient with large positive value, so on and so forth. So now we have some intuitive idea. So I want to avoid my overfitting. I saw the case of this overfitting and I thought, well, in these cases, probably the problem is that I get a very large coefficients. So maybe if I restrict them, I say that I don't want so large numbers like 500,000, maybe I will get something more meaningful. I will force my model to fit these points in a way that looks more naturally. Okay. So now let's check what happens. So what I want is restriction of my parameters, and I can express that analytically in this way. So I'm taking the vector of my parameters, W. I'm calculating its norm squared, and I'm saying, well, I want it to be smaller than some number R that I am defining. That's my parameter of my regularization. What does this mean geometrically? If you think about the space of all possible parameters W that I have. So before, I could use any vector W that lives in that space. That was pretty okay.
And now we restrict only to vectors that are inside the hypersphere of radius root R. Yes, absolutely correct. So I am just making some sort of ball with radius of R around the origin of the coordinates. And I'm saying, okay, now I want my vector to live inside this ball. This means I will make my model less flexible. So my problem was overfit. Overfit means high variance, so my model is too flexible. I want to make it less flexible. To make it less flexible, I'm restricting my parameters of my linear regression. In this case, I'm saying I want my parameters to live inside that ball of radius R. Now, how do we do that? So we have a problem of minimization. We have a problem of minimization of that SSE. Now I'm adding this sort of restriction. So you remember from the previous lecture that this is basically the problem of the restricted minimization. We have considered that, and hopefully you know what to do in this case. So I'm collecting the function that I minimize and my conditions that I have in this case, I am collecting into one entity that is called, who can tell me, who remembers?
Wait, could you repeat? So
I have the problem of restricted minimization in this case. Yes. And I have my SSE, so my error of all that linear regression. And I have a restriction that tells me that all my parameters live inside that ball of radius R. And now I'm collecting everything that into one, let's say, entity that I have mentioned in the previous lectures. And this entity is called?
Probably some error, squared error. No, nothing else. Okay.
Yep. A Lagrangian. I'm collecting them into a Lagrangian. So hopefully you will remember from that lecture when I showed you all that problem with that walls, with KKT conditions, so on and so forth. So we are collecting everything that into a Lagrangian. Dual variables, so hopefully you remember that, or you will remember that. But the idea is that we collect everything into one such entity. That's my Lagrangian. and I will perform minimization of that Lagrangian. and that looks very simple. So here we have some parts that corresponds to the error, and some dual this dual variable multiplied by my condition C. Okay, so let's get very quickly through that. I see that I don't have much time. So this is called the L2 regularization that I showed you. This confining my parameters to the ball of radius R. Here is some sort of picture. So here is my wall that restricts my parameters. Here is the exact minimum that I have if I minimize only my error function. That's where I want to get. And this is the point where do I get when performing that minimization. You may remember from the KKT conditions that in this point, I should have the gradient of the function I'm minimizing, and basically the gradient of this restriction, so normal to this restriction, to lie on one line. So hopefully you remember that. So that's why I get this point and not some different. And performing that, this is the result we get. So you see that it is called rich regression. So I have performed that with some sort of parameter alpha that I have set it to 0.1. This is the strength of the minimization. So that the strength, I'm just defining that. That's my hyperparameter. And you see the result is much better, and all my parameters are inside, well, from 0.2 to minus 0.4. So everything got much better. When my alpha gets to 0, I get what? Original linear regression. So I'm just losing that part that was confining my parameters, and I'm getting just original linear regression. When I get alpha very big, I have a very big influence of that restriction that I have put on my parameters. And it means that basically regression is suppressed. So I don't get anything meaningful from that. Here is an example how is that performed. So here I'm having a simple regression line and rich regression. And when I'm making my alpha bigger and bigger, my regression is more and more suppressed. It still passes through the point, through the center of mass, but you see that the slope, we are getting more and more close to 0. Okay, the other one method that we can employ is so-called L1 or Lissault regularization. So here it is. I minimize the same SSE function, but this way I subject the constraints. Sum of modules of Wi are smaller than some parameter R. Here is the picture for you, how it looks like. And the main feature of this regression, so everything looks almost the same. The main feature is that we can get pictures like this one. So you maybe remember about that subgradients, that picture that I briefly showed you in the previous lectures, but this is the case we use in practice. So we will expect our minimization result to be somewhere here. It's called L1 because you might guess that these are spheres or balls in the space with L1 metric. So if you know that, but the interesting thing I want you to think about, what is so special about these corner points? What's so special about them?
The derivative is not well defined.
Yes. What else? Where do they lie?
They have no normal, no two normals these points. If like
well,
from the side.
The question is much simpler. Look, they always lie on the axis. That means that one of the parameters is equal to 0. It's not close to 0. It's not some epsilon value. It's a definite 0. You can think of that if you think about L1 space when you are adding all that modules like norm of parameter 1 plus 2 and so on so forth. So they will always lie on your coordinate axis. And if you touch with your function some of the corners, you will get your minimum in a place where some of your parameters, 1, 2, maybe more, are equal to the exact 0. And this is a very interesting case because this means that Lessor regression basically eliminates features. In case of ridge regression, you can say that their influence is small, but we can definitely tell how small it is. Maybe that value of that features is big, it's multiplied by that small number and still gets some sort of influence, so on and so forth. This one sets our parameters to a definite 0. Whatever we have measured there, it has no influence on the result. So we are removing some features with the help of Lessor regression. And the reason is we are basically touching these corners with our function that we are minimizing. So that's the main reason. And these definite zeros, they remove that features. And that's very good. So you are you can see on this plot that some features are now equal to definite 0. We have removed them. That may help us to solve the problem if I have some data set and I'm not sure which features are important and which are not. So I can try to remove some unimportant features with the help of the Lessor regression, because I will get coefficients for them equal to 0. I will see that. And here is example of Lessor regression. And please see the behavior of the green line when I'm increasing the strength of that regression. I'm making alpha bigger and bigger. What happens to the line? It gets more and more close to the horizontal line, but at some point it gets horizontal and doesn't change anymore. We have
because we eliminated all parameters.
Yes, we have eliminated the parameter that was responsible for the slope of this line. We have no this parameter anymore. We couldn't do that with ridge regression. I'm increasing the strength, but I never get to the exact horizontal line. It always has some influence of that parameters. Here, at some point, I have removed all the influence of the parameter, and it became horizontal. So this is your tool to remove some redundant features. Here is basically, I know I'm overtaking some time, but only few nice pictures for you, nothing more. Here is some sort of that regression. Here in color, you see the function that we are minimizing. With the green line, you see the trajectory of the minimization if I perform some sort of minimization. And these black circles, they show to me that, let's say, the function, the ridge regression function that restricts me the parameters. So when I'm making my alpha bigger and bigger, so I'm making more and more stronger my restrictions, I get closer to 0. That's in case of ridge regression. And in case of Lessor regression, I have this picture. And you see that at some point, when I had these strengths of regression big enough, I get to the x-axis, and then I stay on that x-axis. It means I have removed one of the parameters. So I know, so maybe you will play around with that for some time. Here is the 3D plot. You see what happens when I'm increasing these strengths of my minimization. And here are function, the original function that I have minimized, and the function that I get, the Lagrangian that I get when I add everything up with that alpha coefficient. Okay. Okay, that's everything that I will skip. And this is the last idea I show you. Well, we saw ridge regression and Lessor regression. And probably you can think, why don't I imply both? And you can. That's called elastic net. And here is an example of how that coefficient, how they change when you use, in this case, ridge regression. So when I'm making my coefficient alpha bigger and bigger, I'm increasing the strength of the regression, and all my coefficients W tend to 0. Here is linear regression. My coefficients, of course, tend to 0, but at some points, you see that they are getting to 0 and staying there. And here is elastic net. When I'm doing some sort of weighted composition of L1 and L2 regressions, and I have a parameter L1 ratio there, and when my ratio is equal to 1, I get a linear regression. When it's equal to 0, I get ridge regression. Of course, in between, I get something in between. Okay. Not getting into everything else, it's just some sort of one more view on the regression. That's probabilistic view, so you probably will see that somewhere. So if you have some line and you are scheduling points around this line with some sort of distribution, you may get with the MLE method that I showed you the same equations for the linear regression. So that's okay. With that being said, let's wrap up. So what have we done today? We have considered linear regression from many different points of view. We saw why linear regression is called linear, and it's not because it draws some straight lines and planes. It's because a linear combination of some basis functions. We saw how to use that. We saw how to use regularization and at least two methods like ridge and linear regression. So probably you will be able to imply that somewhere. And with that being said, I guess that we are more or less done with the regression. If you have any comments or questions, please. If not, then have a nice weekend and see you next Friday.